Okay, so this video just goes a little bit more in depth about this section of properties of surfaces in the friction unit. Um, the coefficient of friction is represented by the Greek letter mu, and this is just a ratio of the force of friction between two objects. The coefficient of friction is going to stay the same as long as you're working with the same objects in the problem. So for example, wood interacting with wood in a problem is always going to have the same coefficient of friction. Wood with steel will have a different coefficient of friction, but it will always be the same regardless of like the size of the piece of wood and the size of the steel. So let me just get rid of that for a second. There are two equations that we use when working with the coefficient of friction. We read this as the coefficient of static friction is equal to the force of static friction divided by the normal force. This normal force can be calculated as mass times gravity. So if you're given the mass in kilograms, you can multiply it by the force of gravity to get the normal force. Similar to that, the coefficient of kinetic friction is equal to the force of kinetic friction divided by the normal force. So in this example, or in this equation, F sub n is still the normal force. Going back to coefficients of friction, this is a table that shows the coefficients of friction. So there are different surfaces. So again, like wood on wood, ice on ice, metal on metal, and then we have metal on metal with like a lubricating factor or non-lubricating factor. This table would give you the values that you would put into the equation for the coefficient of friction. So you'll notice that the coefficient of static friction is always greater than the coefficient of kinetic friction. That's because it takes more energy to get the object moving than it does to continue keeping that object in motion. Trying to think of what else I can say about this section. We consider it properties of surfaces because depending on how smooth the surface actually is, the coefficient of friction will be different. For example, wood can be fairly rough. If you think of like getting a splinter or touching a piece of lumber, it's not always very smooth, whereas ice is very smooth. And you'll notice that the coefficient of frictions for ice is considerably smaller than the coefficient of friction for wood objects. Teflon, that's a non-stick coating on pans. So the friction, we would expect there to be not very much friction for things interacting with anything on Teflon, and we see that the coefficient of frictions are pretty small. That basically brings us to the end of that section of the notes. I'm hoping that that helps a little bit. Basically, the big takeaway is that if you need to have the coefficient of friction, it will be provided for you unless you are calculating the coefficient of friction based on the forces interacting in the problem. So I guess I will stop there. Going through, actually I will go through one of the practice problems that I posted in the slideshow so that that makes a little bit more sense. So I'm going to skip through the first few. I'm going to go to this problem number 3. It says a museum curator moves artifacts into place on many different display surfaces. Use the values in the following table to find the force of static friction and the force of kinetic friction for the following scenarios. So we have a table with coefficient of friction, which we can use as a resource. A says we're moving a 145 kilogram aluminum sculpture across a horizontal steel steel shield. The first thing that we have to do is convert the mass into a weight. So weight is not the same thing as mass, but if we think of weight as a force, we can calculate it as mass times gravity. So taking that 145 kilogram mass and multiplying it by 9.81 meters per second, that will give us the weight, or the normal force, which is, I just have to check back in my notes, which is 1,422.45 newtons. Now that we have that value, we can use the coefficient of static friction and the coefficient of kinetic friction to calculate for the force of kinetic and static friction. I'm going to split this box into two additional sections. This first section will be for the force of static friction, and the second one will be for the force of kinetic friction. The equation that we use is the coefficient of static friction is equal to the force of static friction over the normal force. Using the value from the table, we have aluminum on steel. So my coefficient of static friction is 0.61. We don't have the force of static friction, but we've calculated the normal force. And then when we would rearrange this, I'll rearrange it up there. We would have 1,422.45 newtons multiplied by 0.61. And that gives me 867.69 newtons. So that's the force of the static friction. So really you have to either have a table or you have to be told what these values are in order to use the calculation properly. For the force of kinetic friction, I have the coefficient of kinetic friction is equal to the force of kinetic friction divided by the normal force. So I'm just substituting things in again. The coefficient of kinetic friction for aluminum on steel is 0.47. And we're looking for the F sub k. The normal force is the same thing from the previous part of this. And when we rearrange the equation, 1,422.45 times 0.47, and we get the final answer of 668.55 newtons. So I hope that helps a little bit. Now the following problems are different scenarios. So a steel sword on a steel shield, and we have the coefficient of static friction and kinetic friction in the table. So that should help with the interaction of the surfaces, as well as a little bit of practice with the equations. And I think that's about it. So if I need to go any further, or if we need to do some like office hour check-ins, that's perfectly fine with me.